Welcome to G Fun Facts Online. When we gaze up at the night sky, our Earth-centric bias leads us to view the stars as solitary lanterns burning in the dark. Because our own sun travels through the Milky Way without a stellar companion, it is incredibly easy for us to assume that single stars are the standard configuration of the cosmos. However, modern astrophysics has revealed a universe that is far more crowded, complex, and socially intertwined than we ever imagined. A significant fraction of the stars in our galaxy are actually bound in binary systems, and beyond that, an estimated 10% of solar-type stars reside in triple systems. Yet, it is within the rarest and most intricate architectural triumphs of gravity, hierarchical quadruple star systems, that the true mechanical genius of the cosmos is put on full display. Making up roughly 1% of solar-type stellar systems, quadruple stars are not mere astronomical curiosities, they are extreme cosmic laboratories. Within their gravitational embrace, we can observe the extremes of orbital dynamics, the chaotic exchange of orbital parameters, the bizarre phenomenon of stellar rejuvenation, and the explosive forging of the universe's heaviest elements through thermonuclear supernovae. To truly understand a quadruple star system is to understand a multi-generational, billion-year-long gravitational dance that ends, more often than not, in spectacular destruction. Let us break down the architectural blueprints of how to build a quadruple system. If you were to take 4 stars and place them at random in the vacuum of space, giving them arbitrary velocities, the result would be a rapid descent into absolute chaos. According to the rigid laws of the n-body problem in physics, non-hierarchical multiple star systems are inherently unstable. The complex, unpredictable transfer of kinetic and potential energy between the 4 immense bodies would quickly result in one or more stars being violently ejected from the system, essentially reducing the quartet to a stable binary or a triple system, casting the loser out into the cold void of interstellar space. For a quadruple system to survive for millions or billions of years, it must arrange itself into a strict, nested hierarchy, functioning essentially like cosmic Russian nesting dolls. Astronomers categorize these incredibly stable configurations into 2 primary architectures, the 2+2 and the 3+1 configurations. In a 2+2 system, 2 distinct pairs of binary stars exist. Pair A consists of 2 stars orbiting a shared center of mass, and pair B consists of 2 other stars orbiting their own shared center of mass. These 2 binary pairs then orbit around a grand, central barycenter. From a distance, pair A and pair B act as single-point masses relative to one another, keeping the peace. A famous visual example of this is Epsilon Lyrae, widely known among amateur astronomers as the double-double. However, modern transit surveys like the Transiting Exoplanet Survey Satellite, or TESS, are revealing much tighter, highly interactive 2+2 systems that push the limits of our understanding. Recent discoveries include the immensely compact quadruples known as TIC 392,229,331 and TIC 285,853,156, which have incredibly short outer orbital periods of just 145 and 152 days, respectively. These systems are so wildly compressed that their mutual gravitational perturbations happen on human timescales, meaning we can watch their orbits shift year by year. The other layout is the 3+1 configuration. In this architecture, the system is built upon a hierarchical triple. A close binary pair is orbited by a 3rd star at a moderate distance. This entire 3-star arrangement is then orbited by a distant 4th star. While stable in the short term, the 3+1 configuration is notoriously susceptible to long-term dynamical instability. If the orbit of the 3rd star becomes even slightly too eccentric, it can easily disrupt the delicate gravitational balance of the inner binary, leading to a catastrophic stellar collision or a violent ejection. But the true magic of quadruple star systems lies not just in their physical arrangement, but in their orbital dynamics and the mechanics of chaos. The orbits of these stars are not static, unchanging ellipses drawn on a chalkboard. Because the gravitational pull of the distant components is constantly tugging on the inner binaries, the system undergoes what astronomers call secular evolution, which refers to long-term, periodic changes in the shape and tilt of the orbits that occur over thousands to millions of years. At the very heart of this evolution is a mesmerizing gravitational phenomenon known as the von Zeipel-Lidov-Kozai, or ZLK mechanism. First theorized in the early 20th century by Swedish astronomer Hugo von Zeipel in 1910, and later independently rediscovered by Soviet dynamicist Mikhail Lidov in 1961 and Japanese astronomer Yoshihide Kozai in 1962. This mechanism explains exactly how a distant tertiary body can drastically alter the orbit of an inner binary. In a standard triple system, the ZLK mechanism dictates that the inner binary exchanges its orbital inclination, or its tilt, for eccentricity, which is its elongation. The distant third star exerts a tidal torque that slowly pumps up the eccentricity of the inner binary, making its orbit highly elliptical, while simultaneously decreasing its inclination. Imagine a spinning coin slowly losing its tilt while wobbling more dramatically. When the orbit becomes nearly flat relative to the third star, the process reverses, the orbit circularizes, and the inclination rises again. This cyclic, pendulum-like exchange can drive an initially perfectly circular orbit into a highly eccentric one, causing the two inner stars to pass dangerously close to one another at periastron, their closest point of approach. In quadruple star systems, however, the ZLK mechanism is put into absolute overdrive. Because of the additional degrees of freedom provided by the fourth star, quadruple systems lack the commuting constants of motion that constrain triple systems and keep them relatively safe. When mathematical models expand the Hamiltonian equations to what is known as the octuple order to account for these complex interactions, a startling reality emerges. Quadruple systems are subjected to immensely enhanced eccentricity oscillations compared to triple systems. The fraction of inner binaries that reach extreme eccentricities is significantly higher in quadruples. Furthermore, unlike triple systems, where the fraction of highly eccentric systems eventually plateaus, in quadruple systems, the fraction of systems reaching extreme eccentricities actively and continuously grows over time. The inner binaries are mercilessly driven into chaotic, highly elliptical orbits where tidal friction begins to sap their orbital energy. This intense friction robs the stars of angular momentum, causing their orbits to shrink dramatically. Population synthesis simulations have shown that this exact combination of supercharged ZLK oscillations and tidal friction is responsible for creating the mysterious short-period binaries we frequently observe in the universe, stellar pairs that orbit each other in a matter of mere days. Beyond the ZLK mechanism, compact 2+2 quadruple systems can also become locked in intricate orbit-orbit resonances. Much like the moons of Jupiter, the two binary pairs can migrate through tidal dissipation or magnetic braking until their orbital periods sync up into perfect integer ratios, such as 3:2, 2:1, or 1:1. This resonant capture acts as a gravitational anchor, binding the evolutionary fates of all four stars together in a mathematically perfect harmony. To fully appreciate this harmony, one must realize that the stars themselves are not static billiard balls. They are aging, evolving, and expanding nuclear furnaces. As the millions of years tick by, the most massive star in the quadruple system will burn through its hydrogen fuel the fastest. Once its core hydrogen is depleted, the star will expand outward into a massive red giant or supergiant. If this star were single, it would simply swell up and eventually blow off its outer layers in peace. But in the tight, gravitationally restricted confines of a binary pair within a quadruple system, expanding outward comes with severe, often violent consequences. As the star expands, it eventually fills its Roche lobe, the invisible teardrop-shaped region of space around a star within which orbiting material is gravitationally bound to it. Once the star's outer atmosphere breaches this critical boundary, the material is mercilessly siphoned off by the immense gravitational pull of its smaller companion star. This process, known as Roche lobe overflow, results in massive amounts of stellar material, often half a solar mass or more, pouring onto the smaller companion like a cosmic waterfall. The consequences of this massive material transfer are profound. The recipient star, suddenly flushed with fresh, unburned hydrogen fuel, undergoes a bizarre process known as stellar rejuvenation. From the outside, the star appears to literally age backward, burning hotter and brighter, looking millions of years younger than it actually is. This vampire-like phenomenon acts as a massive trap for astronomers attempting to date stellar populations, as mass transfer binaries completely defy standard single-star evolutionary models. However, mass transfer is not always a peaceful, steady exchange. If the giant star expands too rapidly, the smaller companions simply cannot accrete the incoming material fast enough. The companion star quickly becomes completely engulfed in the thick outer atmosphere of the expanding giant, triggering what is known as a common envelope phase. Friction from moving through the dense, hot stellar gas causes the companion to rapidly lose orbital speed and spiral inward toward the giant's exposed core. This terrifying orbital decay releases an immense amount of gravitational potential energy, which eventually heats the gas so much that it blows the shared envelope completely out of the star system. What remains behind the clearing smoke is an ultra-tight binary consisting of the giant's stripped, dead core, often a white dwarf, and the surviving, battered companion. In a quadruple system, the violent ejection of a common envelope can have massive systemic repercussions. The sudden loss of mass from the inner binary drastically weakens its gravitational grip on the outer binary, causing the entire quadruple framework to rapidly expand, or, in extreme cases, destabilize entirely, sending stars flying into the dark. The ultimate destiny of a quadruple star system is dictated by the mass of its components, and it is almost always explosive. Over billions of years, the stars will eventually die, leaving behind superdense stellar remnants, glowing white dwarfs, rapidly spinning neutron stars, or light-trapping black holes. When a quadruple system evolves into a quartet of dead stars, the gravitational dynamics become terrifyingly violent. One of the greatest unsolved mysteries in modern astrophysics is the precise origin of Type Ia supernovae. These colossal thermonuclear explosions are incredibly consistent in their brightness, so much so that they are used as standard candles to measure the expansion rate of the entire universe. Yet, their exact progenitors remain hotly debated. It is widely accepted that Type Ia supernovae occur when a white dwarf star accretes too much mass from a companion and exceeds the Chandrasekhar limit, which is roughly 1.4 times the mass of our Sun, triggering a runaway thermonuclear fusion reaction that obliterates the star. However, recent groundbreaking observations suggest that up to 85% of Type Ia supernovae actually result from the explosive merging of two white dwarfs, both of which have masses well below the Chandrasekhar limit. These are known as sub-Chandrasekhar mass models. Quadruple star systems have recently emerged as the universe's premier factories for these cataclysmic events. Because quadruple systems force their inner binaries into wildly eccentric orbits via the enhanced octupole order von Zippel-Leidov-Kozai mechanism we discussed earlier, they act as massive cosmic particle accelerators for dead white dwarfs. When two white dwarfs are part of an inner binary in a quadruple system, the distant pair's continuous gravitational perturbations drive the white dwarfs into highly elliptical orbits, bringing them incredibly close to one another with each pass. As they whip past each other at a significant fraction of the speed of light, they disturb the very fabric of space, emitting gravitational waves, which are ripples in space-time itself. The continuous emission of these gravitational waves drains orbital energy from the system, causing the white dwarfs to inexorably spiral toward each other. Taking into account general relativistic precession and tidal dissipation, complex astrophysical models show that the merger rate of white dwarfs is enhanced by a staggering factor of 3.5 to 10 in quadruple systems compared to standard triple systems. We are already witnessing the precursors to these incredible explosions in our own galaxy. In 2017, astronomers utilizing the Gaia ESO survey discovered HD 74438, a brilliant 2+2 quadruple system located in the young open star cluster IC 2391. At only 43 million years old, HD 74438 is the youngest spectroscopic quadruple ever known, and its outer orbital period is a mere 6 years. Advanced supercomputer simulations of HD 74438's future indicate that the outer binary is actively pumping the eccentricity of the inner binary right now. Over the coming millions of years, the massive stars in this system will evolve into white dwarfs, and the intense, inescapable gravitational dynamics of their 2+2 architecture will relentlessly force them to collide, inevitably sparking a brilliant thermonuclear type Ia supernova that will outshine entire galaxies. Amidst all this destruction and chaos, a fascinating question arises. Could planets, and maybe even life, exist in such a chaotic gravitational environment? Surprisingly, the answer is yes. The exact same strict hierarchical rules that keep the four stars from flying apart also create stable, quiet orbital pockets where exoplanets can safely reside. In a 2+2 quadruple system, a planet would most likely be circumbinary, meaning it orbits one of the tight binary pairs. Imagine standing on a world like the fictional planet Tatooine, watching two suns set, but with two more distant suns shining brightly in your daytime sky. The most famous example of a confirmed exoplanet in a quadruple system is Kepler-64b, also known as PH1, discovered by the incredible citizen science project Planet Hunters. Kepler-64b is a massive gas giant that orbits a tight binary pair, while a second binary pair orbits the entire system from a distance of about 1,000 astronomical units, which is 1,000 times the distance from the Earth to the Sun. However, finding these planetary guests is exceptionally difficult. In vast planetary transit surveys like NASA's TESS or the upcoming European Space Agency's Plato mission, eclipsing multiple star systems act as the ultimate astrophysical imposters. When a faint, background eclipsing binary within a quadruple system passes in front of its brighter companions, the slight dip in the total light output can perfectly mimic the transit of a small, Earth-sized exoplanet. Astronomers must utilize highly advanced photodynamical models and ultra-precise spectroscopic radial velocity measurements to disentangle the overlapping, messy light curves and definitively prove whether they are looking at a complex four-star system or a genuine planetary transit. As a fantastic byproduct of this rigorous vetting process, citizen scientists and machine learning algorithms have recently cataloged over 100 new quadruple star candidates within the TESS full-frame images, vastly expanding our map of these complex, beautiful systems across the galaxy. Hierarchical quadruple star systems truly represent the absolute pinnacle of celestial mechanics. They are delicate, billions of years old clockworks of glowing gas and unrelenting gravity, where the slightest perturbation from a distant, unseen companion can ripple inward, fundamentally altering the evolutionary destiny of a star. Through the sheer mathematical beauty of the von Zeipel-Lidov-Kozai mechanism, orbits are stretched, compressed, and flipped, driving stars to share their lifeblood through mass transfer, rejuvenate their dying cores, or spiral into catastrophic, universe-illuminating collisions that forge the elements in our very bodies. As our next-generation telescopes peer ever deeper into the Milky Way, analyzing the spectral fingerprints of millions of stars simultaneously, the comforting illusion of the solitary star continues to completely shatter. The cosmos is deeply, fundamentally interconnected. In the grand, chaotic ballroom of the galaxy, the quadruple star system stands as a magnificent testament to the chaotic, destructive, and deeply creative power of gravity, a four-part harmony echoing across billions of years of cosmic history. Thank you for tuning in to G Fun Facts Online, where we bring the wonders of the universe directly to you.